The title for this talk is Introduction to Capacitor. And basically what we're going to be doing is we're going to go sort of a quick overview of the tick stack, time series data, and stuff like that, just to make sure everybody's on the same footing. Shouldn't take more than a couple minutes. Then I'm going to sort of just explain the capacitor's sort of computational model. So how you should think about, capacitor does things. What can you do with capacitor? Then we're going to hop into a little bit of the TICKscript syntax. So a capacitor has its own DSL called TICKscript, and we're going to get a little bit into the syntax of that. Next, we're going to try to sort of get you up and running and talk about how you install your own capacitor instance. And then finally, we're going to go into trying to get you to write some basic TICKscripts and some UDFs. So the UDFs are user-defined functions. So one of the features of capacitor is you can write anything that's not necessarily a part of the runtime or the environment. You can sort of add to your system. We'll see how you do that. So just to do that quick review of that I always throw, if you've ever seen any of these webinars that I've done before, start with an introduction to what is time series data. So time series data, via the sort of Wikipedia definition, is a sequence of data points typically consisting of successive measurements made from the same source over a time interval. And what this essentially means is if you were to take all the data that you have there, plot it on a graph, one of your axes would always be time. That's kind of the key component to time series. One of your axes, one of the dimensions that you care about is always time. So to give you sort of a good example of something that is time series data, here we have the hashtag royal baby usage over time. So in the x-axis, we've got a bunch of timestamps, and y-axis, we have the number of tweets per hour. So this is a perfect example, a quintessential kind of example of something that is time series data. X-axis time, y-axis some metric. Next, we have this kind of web graph here, where we have, we have friends, we have some like objects that exist in this kind of graph, and we have these relationships between them. So you have friends, you have likes, you have listens, you have watches, you have cooks. And the sort of interesting thing here, or the important thing here, is the relationship between these objects, or between these sort of nodes on the graph, not how that graph changes over time. It may be interesting how that graph changes over time, but it's not something that is sort of the primary focus of the graph. So this is not time series data. The next thing we have here is some typical sort of weather kind of data, where we're looking at temperature, the dew point, and various other sort of things like wind speed. And we can see that this is time series data because in the x-axis we have time, y-axis we have some value. And in addition to that, we have some other things that are probably computed by time on this thing here. So we see like the temperature. Well, we're not necessarily, we are graphing temperature. So never mind, scratch that. The next thing we have here is sort of this like clustering of information. And this is not time series data. There is no time in this graph. X-axis, we have grade. Y-axis, we have athletic ability. We can see that the important thing here is these little groupings, this clustering of sort of information, where we can determine, whether somebody's a jock, a nerd, a iconoclast, or a diva based off of their X, Y kind of coordinates in this graph. So again, this is not time series data. There is no time here. Within time series, there's sort of two major categories. There's irregular time series and regular time series. So regular time series is the first graph that we have up at the top here. It comes in at a regular interval. So every 10 seconds, every minute, every 2 minutes, every 15 minutes, every day, some regular known kind of interval the data comes in. That's for regular time series. So a lot of databases are irregular, or only support regular time series. The reason for that being, if things come in, if timestamp points come in with fixed timestamps, or at a fixed interval, it's a lot easier. You have to store a lot less data. You know exactly how the data will be coming in for the timestamp, so you can structure it around that. So typically, regular time series databases or regular time series has a lot less on-disk sort of representation. The next type of variant what we have is irregular time series, and that is that bottom graph that we have down here. So irregular time series is time series that comes in at irregular sort of periods. So a good example of stuff like this is kind of event data, where you don't necessarily know where an event is, when an event is going to get kicked off. You just know that it will, and you want to graph that event kind of over time. And you don't have this nice sort of regular interval where things come in. So sort of two different flavors of time series. So this is, I believe, my final sort of slide on the time series stuff. InfluxData is a time series data platform. We offer, a suite of tools around time series. We pride ourselves on being particularly easy to get started with. So one of our big things is we want you to go from 0 to information or relevant information as fast as possible. We provide a familiar query syntax. We have no external dependencies. We allow for both regular and irregular time series. We're horizontally scalable. Throw an asterisk up to that. Now that clustering is a paid product. And the final thing that sort of I want to bring or highlight to is this member of a cohesive, we are a cohesive sort of time series platform. So questions that we get all of the time are, why did you build Telegraph when collectD exists or statsD exists? Or why or graphite exists? Or why would you build Capacitor when Spark exists or Sensu or all of these sort of other things? And the answer to those questions is we don't intend to replace those tools. If you're using those tools, we integrate with those tools. However, if you haven't made a decision and you want to get up and running as fast as possible, and you want to have a seamless experience, we wanted to have a way for you to do that. And that means having a collector, that means having a data store, that means having something you can graph things with, and that means having something you can process the data with. And that's why we have each of those components together. So together we have a lot more power than each of them individually. We can control the experience and give you a sort of better experience, a more fluid experience than you would be able to have in something else. And with that, my marketing for the day is off, and we'll be hopping into just a quick overview of the InfluxDB data model, just so everybody's familiar with some of the terms that we'll be using. So we've got a typical time series graph here, and the question is, what components do we have? Up at the top, we have the label. This is called the measurement. In this case, the measurement is called the stock price. The measurement is kind of the high-level grouping for all of the data beneath it. The next thing that we got off to the side is this legend sort of data, metadata. So we have the blue circle and the green square. And these things, this metadata we call, and encoded into the legend, we call tags. And in InfluxDB, tags are indexed values. And that being said, tag keys and values must both be strings. The collection of all of the tags for a particular thing is called the tag set. So, the blue circle is ticker equals A, comma, market equals NASDAQ, and so on and so forth for the others. Next, we have the y-axis values. In this case, they're called price. So probably could have called the thing just stock and the y-axis called price, but it's neither here nor there. These y-axis values that actually store the data, so to speak, are called fields. Fields can store floats, ints, strings, or bools, all of the 64-bit variety. I think strings have a cap at 64K. The collection of all the fields is called the field set, just as the collection of all the tags is called the tag set. In this case, there's only one, but there could very well be many. You could have price, comma, volume, column, anything else you kind of want to throw in as something you'd like to store as data. Finally, we have the thing that makes this time series, which is that x-axis there that has the timestamp, which is the number of nanoseconds, represented as the numbers of nanoseconds since January 1st at midnight in 1970. So the typical sort of Unix epic. Now we kind of bring ourselves of how do we encode all this information textually. So we have a textual write format or an ASCII write format, actually QDF. So we have textual representation of our points, and our textual representation is called the line protocol, and it is as follows. It goes measurement, comma, tag set, space, field set, space, timestamp. And I will note that the timestamp here is actually optional. You do not need to specify a timestamp. So an example point from the slides we had previously would be stock price, comma, ticker equals A, market, comma, market equals NASDAQ, space, price equals 177.03, and then some massive timestamp. So just to give you an idea what a couple points look like, I've kind of lined their timestamps up here. We have 177, the previous point that we had just talked about, and we have one where ticker is equal to AA and market equals NASDAQ, and price is 32, and then ticker equals AAPL, market equals NASDAQ, price equals 45. So this brings me to what is a series, as we are a time series database. And a series is, in our definition, is the measurement plus the tag set, and that represents a whole series. So you can kind of think of a series as all points that have a common measurement and tag set, and in this case, from the graph we have above here, that would be that blue line is one series, and then that yellow line is one series, and that green line is one series. So in this graph here, we see 3 individual series. So on that note, the measurement plus the tag set plus the timestamp represents a single point in InfluxDB. So in that way, you can kind of think of a timestamp as an ID for a point in a series. And that's my sort of just quick overview on time series and the InfluxDB data model. And on that sort of note, we're going to hop into getting into the main sort of bulk of this talk, which is Kapacitor. So Kapacitor is a time series data processing utility. So it's kind of like Storm or Spark or Sensu, and there's sort of a lot of other things there. So what it does is it processes data in either batches or streams. At the moment, it only works with InfluxDB, but in the future, I believe that may be changing, or anything that can emit line protocol, essentially. Processes this data in batches or streams. You can trigger alerts based on dynamic criteria. So if you want to do some processing and then alert on that, if you ever see your number of write errors go over, I don't know, 10% or something like that, you want to trigger an alert and let somebody know. And you can issue various levels of alerts. You can do a critical alert, a log alert, and sort of a bunch of different things. In addition to that, you can transform the data sort of as it goes along with the typical InfluxQL functions. In addition to the typical InfluxQL functions, you can do more than that. We have sort of these Lambda expressions that you can use to do a little bit more complex ideas. It subscribes to data in InfluxDB. So when you start up a Kapacitor process, you'll tell it, I want you to subscribe to all of the data that's coming through, or maybe just a subset. And finally, it can store data that it processes back into InfluxDB. So that may be a little bit hard to sort of think about. And in order to do that, I'll give you a little bit of a visual sort of representation of how the whole thing kind of fits together. In our mind, you have sort of Telegraph or some other collector feeding into an InfluxDB cluster. And then Kapacitor is subscribed to that cluster, all the data in that cluster. So it'll come through into Kapacitor. Kapacitor will do whatever processing it needs to do, whatever alerting it needs to do. And then it can either be done, or it can take that data and put it back into InfluxDB. So in that way, you can kind of think of Kapacitor as like continuous queries on steroids plus alerting and plus a bunch of sort of other things. The design of the capacitor tool has a sort of few components. It has the server daemon, and that's the capacitor D command. So you can configure inputs, outputs, services that you like to use, so on and so forth. In addition to that, you have the capacitor CLI, so it's just a command line interface for interacting with the capacitor D server. So it calls out to the HTTP API of the server. If you'd like to do that yourself, you could do that, but we would recommend using the tool. An important thing to note here is the CLI is not interactive. Within Kapacitor, there's two main sort of ideas. You have a task, which is like a unit of work. So this is something that is defined by a TICKscript. And tasks can either be a batch or a stream, and tasks sort of define or encode a DAG, which is a directed acyclic graph. And we'll talk about what that means a little bit more. In addition to tasks, you have this idea of recordings. Recordings are saved data, and the main sort of motivation behind recordings are you record some event taking place, and then you can sort of iterate on building a script or build this against a script that would be representative example of this alert being triggered or this task being triggered. It's more of a way you sort of build against your or to develop TICKscripts to give you a little bit of interop in doing so. So as I noted earlier, the capacitor computational model is a DAG, which is a directed acyclic graph. So if you look at this sort of image that I have off to the side here, you have data that sort of comes in through node 1 and then kind of trickles down in this interesting sort of graph. So you can fairly easily express sort of these pipelines or data pipelines. So like do this, then this, then this, and then this, and this, which is a very convenient way to think about computation. It makes it particularly useful. And this is a common sort of thing that you see in other sort of stream processing systems. On that note, Kapacitor will allow you to process either streams or batches. And it's entirely possible that one node can accept a stream but emit a batch. And the contrary goes as well. You can accept a batch but emit a stream. So these are sort of the various kind of things you can do with the system. We'll see in a little bit more detail what that means. So we're just going to hop right into the sort of capacitor syntax. It's a little bit interesting. So we use these pipes to sort of delimit these sort of branching in the nodes kind of in that DAG. So up at the top, we say if we wanted to define a batch job or a batch in TICKscript, we would say batch pipe query, and then you give it some InfluxDB query that you'd like to execute. And then you tell it a period and an every and a group by time. And group by, you can do group by time as well as some other tag. So what this is going to do is, every minute, if you go back in time a minute, it's going to execute this query every 20 seconds, going back in time 1 minute. So you'll have this rolling window of 1 minute intervals every 20 seconds, if that makes any sense. Beneath that, we have a stream. So instead of executing that query every 20 seconds, a stream will kind of just continuously allow data to be consumed by it. So we're streaming, and then we do a pipe from, when this is us telling us where we're streaming the data from, and it's doing it from the database MyDB, the retention policy MyRP, the measurement MyMeasurement, and then we have this where condition, which is matching the host tag against some regular expression. And finally, we sort of emit a window. So what this is doing is we accept a stream, and then we're windowing in the data maybe in 5-minute batches or something like that. So this is just a quick sort of intro to the syntax, where we'll talk more about each of these things as we go along. As we just seen, we saw TICKscript. TICKscript is the capacitor DSL. So DSL is a domain-specific language. So we have a language around defining these sort of DAGs. So it sort of allows you to invoke chaining of these things. It has flat scope, and each variable in the scope defines methods that can be called on it. And these methods come in two flavors. We have the property methods. Those are those dot methods that you've seen, so changing properties of a node. And then the chaining methods, which are those pipes that we had seen in there. So it sort of creates a new node. And there's extensive documentation for each of these. We're going to go through and talk about a few of them that are interesting and sort of continue on from there. And sort of finally, the thing I'd like to note about TICKscript is it's a DSL that's used to define directed acyclic graphs, which are used for processing the data. So, your TICKscript is a direct representation of some graph that we call pipelines. So the syntax in TICKscript, you have literals, booleans, numbers, floats, numbers, so you have int64 or float64, strings, time durations. In addition to that, you have statements, variables, and comments. So the script that we have off to the side here at the center of your screen should show all of these components. So up at the top, we have two variables, error and requests. Errors is a stream from the measurement errors. Requests is a stream from the measurement requests. The next thing that we have here is we're going to do errors pipe join. So we're joining errors and requests as errors and requests. We'll give them those names. And we want to join points that are within the same second. So if there's any timestamp that's within the same second, that's fine. And we want to fill any missing values with 0. And 0.0, so that's that float64 of 0. And then we do pipe stream name, so we're just naming the stream that comes out of it. So I think the important things to note here is those slashes give us comments, so we can see, provide prefix names for the fields and data points. We have 1s in the tolerance, which is a time duration. And then we have variables, and we have, I believe that's sort of all of the major components there. And we have statements, those are the final one. So we can see kind of everything coming into play here. We don't have true or false, but you can use those as well. So gonna hop into maybe a little bit of an exercise, maybe less of an exercise, but sort of something to just get you to think a little bit. So we want to write a simple TICKscript that streams data from the measurement mem and issues a critical alert if there's less than, if their free is less than 500 megabytes. So to do that, we say stream pipe from dot measurement mem. And then we want to alert, pipe alert, dot crit, lambda free less than 500 megabytes. So what this is saying here, just to give everybody an idea, is stream data from the measurement mem, and then I want you to issue an alert whenever there's I want you to issue a critical alert when the free value, the free field, is less than 500 megabytes. And what I want you to do with that alert is log it to temp/alerts.log. We can have, there's various ways you can do this. You could have it, kick off a thing to PagerDuty, kick off a thing to Slack, kick off an email. There's sort of tons of things you can do with this. But in this example, we'll just log it. So one thing that may have popped up by now is we have these Lambda expressions. So TICKscript uses Lambda expressions to define transforms on data points, as well as define Boolean conditions that can act as filters. So suppose we have this where statement, we pass in a Lambda to where, and we say where host is equal to server 001.example.com. So one thing that's particularly odd here is you may note that the double quote versus single quote, the quoting rules in Kapacitor can be a little bit difficult at first, but after some time you definitely get used to them. So host is our tag, and the value for host is server001.example.com. So in here, we're evaluating some Boolean condition, right? We're saying when this condition is true. And beneath that, we have sort of another use of Lambda, whereas we're doing crit. Sigma is greater than value. Sigma, where Lambda is greater than, where the sigma of value is greater than 3. So sigma being the standard deviation. In TICKscript, there's a bunch of different node types, and they come into 3 major categories in my mind. You have initial nodes, so that would be batch or stream that we've seen. So you can accept things in batches, or you can send data to InfluxDB in batches or as streams. The next thing that you have is these interior nodes. I've listed a few of them here. There's way more than I've listed here. So interior nodes can be things like computing the derivative, evaluating some Lambda expression, grouping something, grouping incoming data appropriately. You have where nodes, which we've seen a little bit, where you can apply some sort of SQL-like where condition. We have a window node where you can window data that's coming in. We have an InfluxQL node that can perform all of the various InfluxQL functions on the data that's coming in. We have join nodes that you can join 2 streams of different data sources. We have union nodes, which will perform the union of the 2 things. We have sample nodes, which will sample data at a particular rate. And we have UDF nodes, which allow for defining sort of custom data logic or custom processing logic that you can sort of do yourself. I believe at the moment there's only 2 supported languages for UDFs, and those would be Python and Go. And finally, you have things like output nodes, and these are, alert nodes or HTTP output nodes or an InfluxDB output node. So the major categories here again are we have like initial nodes, we have interior nodes, and output nodes, or we call them terminal nodes maybe. And on that note, we're going to sort of just hop into a couple of the different node types and talk about them. So we've seen this one before. This is a batch node. So a batch node is an initial node in the capacitor DAG, so the directed acyclic graph that Kapacitor TICKscript defines. It takes in an InfluxQL query and performs operations on the whole batch of data returned by the query. And it also provides utilities for describing the frequency and periodicity of the batch query execution. There's a lot of words going on there. But if we look at what we have, just to talk about it a little again, we say batch, pipe, query. We give it an InfluxDB query. So select mean value from telegraph.default.cp usage idle, where host is equal to server A. And then we want to run that with a period of 1 minute every 20 seconds, grouping by 10-second intervals and the various CPUs. The next thing that we have is a stream node. So a stream node is an initial node in the capacitor DAG. It takes a stream of data from a particular measurement and performs operations on it. So what I'm saying here is stream pipe from database.mydb, retention policy.myrp, measurement.mymeasurement, where.some condition, so where lambda, where host it matches some regular expression, and we want to window that data in some way. So this is kind of just what a stream node looks like. The next thing that we have here is an alert node. So an alert node does exactly what you would think it does. It issues alerts. So to get an alert node, I'd say stream.groupByService, and then I can do pipe alert and do some friends, and I say .id. So this is me giving the stream an identifier. So I'm just some way to identify the alert. The next thing I have is the message. So this is the actual message that comes out of the alert. You can give it a sort of template where you can have the particular values that you'd like to come out of it. And then beneath it, we have 3 sort of levels, alert levels. You have info level, warn level, and critical level. So if value is ever greater than 10, you want to issue an info alert. If value is ever greater than 20, you want to issue a warning alert. And then if it's ever greater than 30, issue a critical alert. And you can tell it where you'd like to issue those alerts to. So in the example below, we see this is going to issue 2 post requests. It's going to issue a post request with the alert to example.com/API/alert, as well as another example.com/API.alert. So you can issue 2 of those out. And then finally, we issue an email to oncall@example.com. So in addition to the posting to a particular endpoint and sending out an email, we also allow you to use OpsGenie, PagerDuty, Sensu, Slack, VictorOps, Alerta, email, exec, HipChat. Any of these things you can use to sort of, you can alert to any of these things via this sort of alert node here. And there's a lot more than I've listed here. I've just picked the ones that seemed most prominent in my mind. The next thing that we have is a where node. So a where node filters incoming data according to some Lambda expression. So the example that we have here is we make a variable called sums that is a stream node where we're streaming from everything. So this means we're streaming everything. So it just gives us everything in the database, but group it by service and host. And sum together all of the value, all of the values. So this is just summing together everything that's coming in. And then once we have that, we can add sort of additional conditions onto that. We want to sum something where host is equal to h1 example.com. So anything that has hosts h001 example.com, we want to sum the values together and issue an alert for anything to this. So where nodes filter incoming data according to some Lambda expressions. Important thing to note there. The next thing that we have is a window node. A window node bundles data together. A window's period specifies the amount of time of data that will be yielded to the pipeline. A window's every specifies the frequency at which the data will be yielded. So if we look at the example above here, we have stream pipe window dot period 10 minutes dot every 5 minutes. So what this is saying is every 5 minutes, go back and give me a 10-minute window. So here we'd have every 5 minutes we have kind of a rolling 5-minute, 10-minute. We have a rolling 10-minute window that executes every 5 minutes. So suppose your data comes in at some fixed interval. Half of your data from the previous window would be in the next window as well. The next thing that we have here is the join node. So if you're familiar with the idea of joining data, that's exactly what this does. We can take 2 input streams and join the data on their timestamp. We're joining on time, I should note that. And you can specify a tolerance for joining on the timestamp. So points that come in within 1 second of each other are considered to be the same time. It's an important thing to kind of note there. To use a join node, you define one variable, you define one stream, you define another stream, and then you say, pick one of the streams and join it with the other. And you can really do these in either order. I could have joined requests with errors or errors with requests. Either one works. Now that we've got an idea of what some sort of TICKscripts look like, maybe not in quite ton amount of detail, but we're at least familiar with what things are, what kind of nodes there are, and how you use it. We're going to hop into actually using capacitors. So how do I use capacitor? And the process is sort of like this. You create a TICKscript. So in this case, we're making a TICKscript called CPU_alert.tick. Tick's the file extension that we use for TICKscript. And suppose that had the following TICKscript below, which is a stream from measurement. I want to stream all the data from the measurement CPU, and in particular, I want the measurement, the data where the CPU tag is equal to CPU total. And it's a little bit confusing because telegraph does something that's a little bit non-standard. And then I want to issue a critical alert when usage idle goes above, say, 70. And we're just gonna keep logging this to temp alerts. So once I have this TICKscript, I'm going to define a capacitor task. And to do that, I use the capacitor CLI and say capacitor define -name CPU alert. So this is me giving the task a name. I'm telling it what type of thing it is. So I have to say type stream. Then I have to say -tick, and that's giving it the TICKscript. So I give it CPU alert.tick. And then finally, I tell it what things it's allowed to stream from in that dbrp. So I'm telling the task what it has available in its scope. So this can never pull anything that's not in telegraph.default. It'll only ever pull data from there. So this allows me to define my task. Now that we have the task kind of defined, that's all that's up there, we can list the tasks. So I can say capacitor list tasks. And when I do that, I should see kind of this output at the very bottom here, which is name, type, is enabled, executing, database and retention policy are the things that should be there. And I should see CPU alert, stream, false, false, telegraph, .default. So it's not enabled, it's not executing, it's a stream, and it's called CPU alert. So if I wanted to sort of test against this, suppose that I want to test my TICKscript against some sort of scenarios, I can record a stream. To do so, I would use the capacitor CLI to issue a record command. So I'd say capacitor record stream -name CPU alert 20 seconds. So that just allows me to record a stream called from CPU alert for 20 seconds. And it returns me some recording ID. So I take that RID and then I say capacitor list recordings, and that will show me all of the recordings. It would output that RID that I had done there. And once I want to sort of iterate on this alert or this TICKscript, I could say capacitor replay, give it the IT I'd like to replay, and specify the TICKscript or the task that I'd like to replay it against. And there's that -fast flag that we have there that says I want you to run this as fast as possible rather than at the same time that it happened. That's just a sort of quick aside for recordings. You should definitely play with them a bit more if you are interested in iterating on that. The next thing you can do, other than record something, make a recording of a task, you can show a task. So to do that, you use the show command in the capacitor CLI. So you say capacitor show CPU alert, and you should see something that executes like this. And the important things to note here are the enabled and executing are both false. Below we can see the TICKscript, so that we had to define the task. And then finally, at the very, very bottom, we can see a dot diagram that describes the DAG, the directed acyclic graph that the TICKscript represents. So as you can see, we really just have the source stream that reads to stream 1, and stream 1 leads to alert 2. Now that we have sort of our task in there, we can enable our task, and to do that we issue a capacitor space enabled space. Maybe it should be enable, that's a typo of mine. Let's fix that. So capacitor enable CPU alert. What we're telling capacitor now is we want you to make this alert that this task we had just defined go sort of live. And once we do that, we issue the capacitor show CPU alert command again, and we should see the exact same thing that we saw previously. The difference being that enabled and executing have toggled from false to true. So this task is actually being ran in the database. So the next thing I'd sort of have you do, if you have a thing open, or you can just sort of think about it, is define a task from off of the following TICKscript. And rather than sort of make you sort of go through the whole process, we'll just hop into that solution, which is you say capacitor define dash mem alert. You could have called it something else. It's a stream. We're calling it mem_alert.tick, and we're allowing it to come from the telegraph.default database and retention policy. And kind of this brings me, all of the stuff that we've been talking about is sort of, the baseline sort of use of telegraph, or of capacitor. The real sort of functionality, or the sort of power of capacitor comes out of what are called user-defined functions. So things get a little bit more complicated here, but a UDF is a user-defined function, meaning you can write your own functions, algorithms, whatever you sort of want to call them, and plug them into capacitor. And your custom functions run in their own process and communicate with capacitor via some sort of protocol, through protocol buffers, and then I can show you the interface that you have to implement. And the important thing here is any programming language that supports encoding and decoding protocol buffers can be used to create a UDF agent in capacitor. And currently the only supported ones are Go and Python, but we'll be adding more languages and as things go along, and we happily accept PRs. We're going to sort of go into a UDF example, and in that example, we're going to be using Python. So hopefully you have some familiarity with Python. If not, you should be okay anyways. Python's pretty easy to read. So UDF node has a little bit of a different syntax than regular things in TICKscript. So we have some example of a TICKscript here. We say stream pipe from all the other stuff. And then the thing that we denotes a UDF is this @ symbol that we have here. So the @ symbol means that this is defined outside of capacitor land. This is defined some user-defined function, and we'll see sort of in more detail how to do it. But this will just give you an idea of what a UDF looks like in capacitor. So the process for writing a UDF, or the steps you go through to write a UDF, are pretty simple. There's just 3 of them. It is implement the UDF handler interface, and we'll see what that is in just a second. Write a TICKscript that uses the UDF, configure the UDF inside of capacitor. You do all those things, and then you have your UDF in capacitor. So on implementing the UDF handler interface, there's a few methods that must be implemented. For the most part, implementing the interface should be very, very easy. The hard part is getting the whatever you're doing to do what you want to do. So, if you want to do some machine learning on the thing, that should be hard. Implementing the interface should be trivial. So, the interface has a sort of suite of methods. One of the methods you must implement is the info method. So the info method is called when capacitor is started, and capacitor uses the info method to parse the options associated with the UDF. So those dot methods in TICKscript, and the info method specifies whether or not this node wants or provides what types of data it wants or provides. So does it want a stream? Does it provide a stream? Does it want a batch? Does it provide a batch? Does it want a stream but provide a batch? Kind of stuff like that. All of this kind of stuff is defined. All these aspects are defined inside of the info method. The next thing is you have the init method, which is run when a task containing the UDF starts executing. So the differentiating things here being info happens when capacitor starts, init happens when the UDF starts, or when the task containing the UDF starts, that is. It receives a list of specified options that are pulled from the TICKscript. So it gives you a map, I believe, of the various options. Then the next method that you have is begin batch. So this method should only be used if the UDF wants or receives data in batch form. So if it's data that's being handed or sent to it is batches of data, not single data points, you'll want to implement the beginning batch method. If it does not accept batches, then this method can simply be a no-op. The next one we have is an end batch. So this method should be implemented or used only if the data provides or sends out data in batch form. So if you work exclusively on streams, you don't need to implement either of these methods. And finally, there's the point method, which should be used if the UDF wants or provides data in stream form. So depending on what you want to provide or you'll want to implement these sort of different methods. The final method that we have here is, I've seen a lot of people just don't bother implementing it, but I recommend that you do, is a snapshot and restore. So if the process for some reason gets killed, you can save the state of it rather than it just going out and you losing that data. So if you implement all of these methods to some extent of implement, you should have everything necessary for creating or putting your own UDF into Kapacitor. So there's two examples that we have in the sort of Kapacitor repo here. I would highly recommend that you go sort of take a look at them. And once you've written your UDF, you're going to want to configure the UDF. And yeah. So we're going to start here. So we have an exercise that says we want to create a TICKscript that uses the moving average UDF in the Kapacitor repository. If you'd like to pull that down, you can do that. Take a look at how it's implemented. We won't cover that here. Then we're going to configure the UDF in Kapacitor. We're going to create a task from the TICKscript and then enable the task that we created. So the first thing that we've got to do is create a TICKscript that uses the moving average UDF that's in the Kapacitor repository. So if you want to do this yourself, you can do this. All of the logic for that is in the Kapacitor repository. And to do that, we're going to say, I want to stream from the measurement CPU, where CPU is equal to CPU total. And then I want to run pi average, which is like a moving average function on the stream. And that's going to grab the field usage idle and say, I want the window that I'm averaging across to be 10. And I want to output that thing as CPU average. And when I'm all done with it, I want to just write that data back into InfluxDB. So once we have the TICKscript, we need to configure the UDF inside of Kapacitor. To do that, in the Kapacitor config file, or the TOML config file, we will modify the section that says UDF, in particular the section that says UDF functions. So what we're going to want to do is set up prog, which should be the path to the program that is responsible for running the UDF. So in this case, that is Python 2. And then I want to specify any args that should be passed to the program. And in particular, I'm specifying -u and then the path to my program. So this to the UDF Python code that has been written. And then I want to specify a timeout, so what to do if nothing's happening in 10 seconds. And finally, I want to use the, I need to specify the environment that it runs in. In this case, Python path is the thing that I kind of listed here. And that is the path to the agent, UDF agent for the process. Once I've done that configuration, I want to open up a capacitor. I want to start capacitor with the following toml. So to do that, I say capacitor space -config, and then I give it cap.toml. Now that I've created the TICKscript and I've started up capacitor again, I can enable the task that I created. To do that, I'm going to say capacitor define -name CPU average -type stream -tick CPU _avg .tick -dbrp telegraph.default, and then I enable the task by saying capacitor enable CPU _average. And that kind of brings me to the end of things. And if we kind of just summarize what we did, again, I'll go to this over here. Start here. We wrote a UDF, and to do that, we say the sort of steps you'd go through for that are implement the UDF handler interface. We write a TICKscript that uses the UDF, and then we configure the UDF inside of capacitor. And once we do that stuff, we're kind of have our own UDF in use in capacitor. And kind of on that, just going to sort of summarize of what we went through again. We went over a quick overview of the tick stack inside our time series. We explained the computation model of capacitor. We talked about TICKscript syntax. We talked about some of the things that you do, how to enable tasks, how to run a sort of a capacitor instance. And finally, we got into, writing your own TICKscripts or, writing UDFs with capacitor. And